This video is going to show you how to build and align the brand new CFT1 compact field transceiver, a 5-band QRP CW Field Transceiver that was designed by KM4 CFT in Colorado. This transceiver covers 40 through 15 meters and is designed primarily to be a very efficient, very easy to use field radio for operating CW from either summits on the air, parks on the air, or any other field radio operation. Jonathan's put together a really nice 50-page assembly manual, so even though there isn't a whole lot of assembly to do here, it's a very, very detailed manual that will walk you through every step of the assembly. And I'll show you that in this video. The kit itself comes with 4 circuit boards, 2 of which become essentially the front and rear panel of the radio, and the other 2 are actually the radio itself. The internal boards are a mix of surface mount and through-hole components, and all of the surface mount components are already pre-populated on these boards. So the only soldering you need to do are for any of the through-hole components. And of course all of the parts, including passive components, inductors and capacitors, there's one PNP transistor and an LED, a MOSFET, and then the rest of the hardware, a couple of encoders and switches, some of the screws and nuts, and of course the toroids for winding the toroids and the crystals. Now I will say, if winding toroids is not your thing, Jonathan does sell a kit of all the toroids pre-wound for $30. Or if kit building isn't your thing, but you do like the idea of a field transceiver, it is available fully assembled and tested as well. The first step with any kit is to ensure you've got all the pieces and parts, the 4 circuit boards, as well as all of the components. So it's very easy to match up the components themselves with this illustration here. The next page lists what all the values are of all the components. The first step is to do a little bit of cleanup on the boards. There's these little features that were used to essentially snap the boards apart after they were manufactured. He calls them mouse bites. And you can kind of see them on the edge of the board here. And you want to kind of clean those up to smooth the edges of the board, because essentially these edges are going to be the outside edges of the assembled radio. This cleanup can be done with a hobby or an X-Acto knife, or a knife like this, and just to kind of slice them off, or actually be done like I'm going to do it with a small file. The next step is to install and solder the 4 molded inductors onto this circuit board. And just like the rest of the manual, all of the components are highlighted in red and make it very easy to identify the mounting locations on the circuit board. Now you'll notice on the silk screen that one of the 2 holes for the inductors is surrounded by a semicircle, and the intent is that's where the body of the inductor will mount when you put it in this vertical orientation like that. And then simply repeat that for the other 4 inductors and solder them in place. Be sure to save some of the clippings off of the leads, because you're going to use them later to help ground all of the crystals together. Now the next thing is to install 16 leaded ceramic capacitors. Those 16 capacitors consist of 10 different values. So it might make sense for you to sort them all by value first, and then just go line by line, installing each one in their designated locations. Note that some of these capacitors will come in some cut tape, some will come as loose components. And the way to read the numbering on all of these capacitors is to look at the digits. Like this one, if we can see through the camera here or not, says 121. That means that it's 1, 2, and then the last one means 10. So that'll be 120 picofarad. There's a single capacitor that's a 20 picofarad cap, and that one just says 20 and J for the tolerance. You may need a magnifier to measure some of these physically smaller capacitors to get the value off of them. Or if you've got an LCR meter, you can measure them to be sure. And finally, some of the capacitors may have their leads kind of bent a little bit wide like this, and you may have to straighten those out to kind of make them straight coming off of the capacitor itself to make them fit the holes of the board. Now the labeling on the capacitors is indicated here in the table as well in the assembly manual. So for example, the 100 nanofarad cap, one of those is a 104. The 150 picofarad caps are labeled 151, and so on. Now when I put some of these smaller capacitors in the board, I just bend their leads ever so slightly, as you can see, to keep the capacitors from falling back through the board before I solder them. When I've got the first half of the caps installed, the next two are the two that have got, or two of the ones that have got the wider legs. So I'm going to have to straighten those out to fit them into the board. I'm just going to use a pair of relatively smooth jawed pliers, or at least use the smooth portion of the needle nose plier here to grab these leads and just flatten them out and get them straightened out to put into the board. Alright, I've got all 16 capacitors installed, and I really have to say that Jonathan's done a really nice job designing this board, and that all the capacitors are very clearly marked. They all have squares around the capacitors themselves, so it's really clear the orientation. And most importantly, he's left a really nice, good-sized annular ring, to solder all of the parts on there with enough room to get a decent solder fillet. So really nice job putting this board together there, Jonathan. Now the next step is to install the 4 crystals onto the board right here. Now, similar to when I installed some of the capacitors, what I did is I put each crystal you put in place and just pull the leads, kind of tight and diagonal out a little bit so that the crystal will stay flat against the board when you solder it down. I find it's probably best to do these one at a time so that none of the other leads get in your way. Now, with the 4 crystals soldered in place, the next job is to take some of the lead trimmings and solder a bridge, essentially a bare wire, shorting the tops of all the crystals together, and then take another piece and go from this ground hole here up to the case of the crystals themselves again. Now for this, it may be helpful to put a small blob of solder on the top of one of the crystals first. So it may take a little bit of extra heat here to get this the solder to stick. Once you got the blob on there, then we can lay our wire in there and solder it across all 4. And then finish the soldering job on the top of the other 4 crystals. And then we complete the job with one more wire going from the ground contact on the board up to the crystal itself. Now next we install the MPS 751 PNP transistor. It's a TO92 case. It's got a flat spot on it. That flat spot corresponds to the flat side of the silk screen right here. Right, the 2 electrolytic capacitors are next. They're located down here, and they are polarized. If we take a look at the capacitors themselves, there's a white stripe with a negative, indicating the negative side of the capacitor. The other side is the positive. And if we look at the board, we can see that their positive is a tiny little plus sign right there. The negative side has got the white silk screen around it. So the positive on this side, negative here, positive down here, negative up there. The next thing to solder in is this barrel jack for the power, and it's got a couple of tabs that go into these slotted holes here. Now you'll notice when you put it in there, there's a little bit of slop in it, okay, because the holes are a little bit bigger. So you really want it to be perfectly straight so that the case fits properly. And you can do this a couple of ways. You could put it in and just solder like one of the tabs and then bend it so that it's nice and straight. But you can also use one of the 3D printed halves and slip it over there and fit it right on top of the jack. And you can even tape this in place so that the jack is exactly where you want it. And with this taped in place temporarily, we'll go down and solder that. I have to say, taping that case half in there temporarily to hold the jack in place actually worked out perfectly to get that aligned to solder it properly. Next up is the B and C connector for the antenna. That goes in on this edge of the board, and even though there isn't as much slop in that, I'm going to tape on the case half again just to be sure it's perfectly aligned before soldering it. Now next up is this 2x11 pin socket. This gets soldered on the board here, but it goes on the opposite side of the board, not the same as the component side. So flip it over and install that connector here and then solder it from the other side. Okay, after soldering, it should lay flat on the board like that. The next step involves installing the IRF 510 MOSFET, and this involves using the MOSFET, the board, a M3 by 10 millimeter standoff, a grommet, a collared grommet, an M3 by 6 millimeter screw, and an M3 nut. First we secure the standoff to the board using the M3 nut on the reverse side. Then you want to take the MOSFET and bend the leads, kind of as shown here. There's a pretty good diagram in the assembly manual that's just about full size, so you can actually hold this up against it. I found that by getting the leads, to bend the leads close to the body, I just laid this the part with the leads right on the edge of the desk. I was able to bend them that way, and then used my blunt needle nose pliers to make the final bend. And the idea with this is that when this gets mounted to the board, the leads go in the hole here, and the top of the MOSFET fits right on top where that standoff is. But first, we need to install the grommet. So this collared grommet, if you look at it, it's got a little bit of a thin collar at the top, and that gets inserted on the top of the heatsink here and goes through that hole. So it sits nice and clean on that, and basically flush on the other side here. And then this whole thing fits into the board with that grommet in place. And then we can take our 6mm M3 screw and attach this down to the standoff. Now the important part about this assembly is that the top surface of the MOSFET and the tab, you want that to be parallel with this board, because ultimately when the back panel goes onto this assembly, when we stack the radio together, we want this whole surface, the heatsink surface of the MOSFET, to sit against the heatsink pad that is part of the bottom PCB. So we want to make sure that this is parallel. If you've got to rebend the leads in order to make that happen, go ahead and do so. But ensure that the back of the MOSFET is parallel to the circuit board surface. Once you're satisfied that the heatsink surface is parallel to the circuit board, you can then turn it over and solder the leads in place. The next step is to wind the toroids. There are 6 toroids to wind, and also 1 Bifilar transformer. The method for winding each is the same. The instructions actually give a link to a video that I did several years ago to show how to wind toroids using a sharpened chopstick in a bench vise or a machinist vise here. Makes it really easy to hold the toroid when you're doing the winding. So I'll show you the beginning of that process in this video. If you want a more complete tutorial, go visit the video link that's in the assembly notes. The toroid core and the wire length needed to do the number of turns indicated is indicated in the table, so it's really easy for you to prepare the amount of wire you need and wind each of these toroids. You want to try and get the wire windings evenly spaced across the toroid, and to have the leads kind of come down in parallel to each other on either side of the core. It'll make it easy to solder into the board. So again, I'm using a sharpened chopstick here, and I've got a couple of different ones that I've sized for different size cores. This is a T30, and that fits nicely on this one here. So you can start either by passing your first turn up through the core or down through the bottom, whichever one you prefer. And again, every pass through the core is 1 turn. So that essentially counts as my first turn. I've got to do 9 for this first coil. So we'll take this and pass this through the top here for the next turn, and then pull it down, and then work our way all the way around, doing all 9 turns. So now I've got 2 done here, and I'll grab the next turn here, rotate the core around a little bit, and drop the next one down. So there's 3. And 9. Now that I've got my 9 turns on here, I'm going to pull it off of the stick and spend some time making the turns evenly spaced across the core. This is just a manual operation in your fingertips with your fingernails. And that looks pretty good. I'll probably tighten these up a little bit more, but let's just double check the turns count. So again, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 turns. So that's L18 is done, and just 5 more to go. And there we have all 8 toroids wound. It looks like a very tedious job, but the whole thing, to wind all of them, took me maybe 15 minutes. Now before we install the toroids on the board, we need to strip away the insulation. Now, the insulation on these wires can be stripped away one of two ways. One is to kind of scrape it with a razor or X-Acto knife, but the other is take advantage of the fact that they can be heat stripped. And basically taking a soldering iron with a blob of solder and kind of bury the wire in the blob of solder. The heat will boil away the insulation, and as you move back and forth, it also has the benefit of tinning the lead at the same time. So that's the method we're going to do here. Get my blob of solder there, bury the wire in the blob, and just work it back and forth a little bit. Alright, there's L18 installed, and just pulled the toroid close to the board and soldered it off. And once it's soldered in place, you can then go through with a sharp pointing object like a toothpick and even the turns out if you want. So I may go through and retouch those up after I install the other 5. When soldering these in there, because of that enameled wire, it's a good idea that once you've got the solder melted, just leave the iron on there a few extra seconds to ensure you boil off any remaining insulation that might be on that wire. Okay, that takes care of winding, stripping, and installing all 6 of the toroidal inductors. The next step is the Bifilar transformer. The Bifilar transformer is wound on a ferrite core, which is just kind of plain, kind of dull gray. It's a little bit larger, make it easier to wind. And the Bifilar means that it's a pair of wires being wound on it together. So Jonathan provides you with a hank of wire, one with gold insulation, one with red. It's kind of pre-twisted together, and you wind all that together as if it's one wire. And then we'll use the colors to separate the windings later on to insert into the board. The winding technique is the same, except there'll be 10 turns on this core for the transformer. Now, the installation of the transformer, Jonathan did a nice job here. You can see the letter G right here. That's for the gold wire on this side of the transformer, and the letter R right up there. So the red and the gold wires for this side. He did the same thing over here. You can see the G right there and the R right up over here. So just take some care when installing the transformer, and also be sure that when you strip the wires and when you solder them in, that the solder doesn't leach up and short either side of the 2 windings together. But other than that, this is probably the most tedious part of the entire assembly. Now that all of the toroids and transformers are wound and all installed, the rest of it is pretty straightforward. So that completes all of the soldering and assembly work on the RF board. And next we turn our attention to the control PCB. And the first thing we'll do on here is install the 2 3.5mm jacks, one for the key, one for the headphones. Now here I'd recommend soldering just 1 pin of the jack first, and then turn the board over. Make sure the jack is straight. If it's not, kind of push it back and forth in place. Then flip the board over and solder the remaining pins. Right, next is this little 2x3 header, and same thing, I'd recommend kind of putting it in place, soldering 1 pin in place, making sure that it's laying flat and parallel to the board, and then if not, making an adjustment, and then soldering the remaining pins. Next is the power switch, and generally for any of these things that have got some external access, like the power switch and the jacks, I've been putting a little extra solder on them, mainly because these are going to be accessed externally, subject to some vibration and some stress, so a little extra solder to give you a little more mechanical strength isn't a bad idea. Alright, next up is this 2x11 pin header, and that goes just opposite the switch here. Now if you look carefully at this header, you'll see there's a bit of a shoulder on one side and not the other. So the part that does not have the shoulder is what goes through the board. The part with the shoulder sticks up above the board. And when you solder this, the pads are pretty close together, and there isn't a very big annular ring around each of the solder locations on the other side of the board. So you just want to take some care that you get good solder joints at each one of them, and that you don't have any solder bridges. With something like this, I typically start soldering just 1 pin on either side, diagonal opposite corners, and then turn the board over and just make sure that the header is sitting flush and square and if not, it's very easy to reheat one of those joints and reposition. If you're satisfied with it, then go ahead and complete the rest of the solder joints. Now you do want to trim these leads flush, and there's a bunch of them, and they're really small and they're kind of thick, so be really careful these things don't go flying into your equipment or your eye or any other project that you're working on. Next up is to install the LCD panel to the control board. It's actually done using this header, but it's soldered on the opposite side of the board, or installed on the other side of the board. You can see the outline for the LCD panel here. The header has got a long side and a short side. The short side is what goes through the board here, and then we'll turn it over and solder the other side. I recommend soldering one pin first, making sure it's straight and flush, and then soldering the remaining pins. Now, the instructions say to install or secure the LCD with these 10mm screws and nuts, and to use some Loctite or some thread locker, but I couldn't find any here. So instead what I did is I made up some spacers with some old fiber washers that I had here, or actually nylon washers. So I filed some down to make the right spacing here so I could secure the screws a little bit tighter and not stress the board. So, but that was just my solution here for not having any Loctite. After soldering the LCD panel, the next step is to trim off the excess length of these leads. And again, these are pretty thick leads, so you want to be careful that the little ends that you cut off don't go flying somewhere. Use some eye protection and just keep track of where all these things go. I do mine typically over the top of a garbage can, so they go right into the can. The next up is the volume potentiometer, and it's got a couple of snap kind of pins on it. So it kind of snaps itself into the board. So once you get it in and flush, just flip it over and solder it in place. Next up are the 6 push-button tactile switches, and they go right on the board here. And again, these also have got these pre-bent leads, so they should snap right into the board and hold themselves in place when you solder them on the opposite side. And that's quite convenient that they all hold themselves in place like that for you. Okay, next up is the LED. The LED is polarity sensitive, so the longer lead is the anode. That's the plus side that goes over on this side here next to the plus. And then you also install this 4.5mm spacer between the LED body and the circuit board to space it up properly. Now, the last part to be installed and soldered in the board is the encoder. And notice it's got 3 electrical leads on one side, 2 on the other, and then the 2 spring clips. And again, they'll snap into the larger holes on the side of the board. And that part holds itself in there nicely, ready to be soldered. And with that, the soldering is now complete on both boards. So I'm going to take the time to go through and just clean up some of the flux on these boards. I already did the RF board. I'm going to clean up some of the solder flux that's left over on the board here, just so I've got a nice clean assembly when I go to put it all together. Now, before we apply power, we'll do a quick electrical check. Basically, first thing is just fairly carefully inspect your boards under magnification and light, especially the solder joints around the transformer, because that's easy to kind of get some solder bridges there. And then there's also some basic resistance checks between the ground and 12 and 6 volt, and between the supplies directly, both on the RF board and the control board, and they're indicated right here. So you can very quickly just take your multimeter, and in the case of the RF board here, I'll touch ground, 6 volt and 12 volt, no shorts. Okay, again, no shorts. So I think the basic quick smoke test, just to ensure nothing's going to go bang, is complete. The next part of the electrical checkout is just to set the LCD contrast. For this, you're going to be supplying 12 volts through some clip leads, as shown in the assembly manual from the power switch and this header. And then once you're doing that, the LCD screen should come on, and there's a small adjustable resistor, RV4, on the back side of the board that you'll use to adjust the contrast of the LCD. Now, of course, this is on one side of the board, the LCD panel's on the other, so you have to be doing some flipping back and forth to get the contrast set right. Now, when I first powered mine on, the LCD lit up here, but there's no characters displayed at all, so the contrast is off quite a bit. So I'll stick the trimmer very carefully in this very tiny potentiometer back here. And now if we turn it slowly, there we go. Now I've got some digits showing. If I keep going, eventually the background shows up here. So what we want to do is reduce it till that goes away, till we get some good contrast. So now I got the LCD contrast where I need it. Alright, now it's time for some mechanical assembly. So there are three kind of frames, if you will. They're all 3D printed. And the first one we're going to grab is this one here. This has a little bridging piece on it that's a little detented this way. So the orientation we want to use is on the table just like that. And we'll place 4 of these standoffs in the holes. Okay, the next step is to take that frame, turn it over, and take our control board and fit it on here. Now there are 3 notches, one for the switch and 2 for these jacks. So you just want to carefully kind of get them through there. Don't push too hard because you don't want to break the print, but it should slide on there real nice. Just like that. And we'll secure this in place with the remaining of these 4mm standoffs. Next we take the front frame, and that gets pressed on top of these standoffs. Now you'll notice that there's no notches in here, but there are 2 small little notches right here, and those go over these solder joints here, and then the whole thing should press in place just like so. Next up is the front panel PCB. But before you put it on there, make sure you remove the nut and washer off of the encoder. And then the front panel circuit board drops right in place. Everything should line up perfectly. If your LCD panel doesn't fit through the hole, you may have to adjust the opening with a file. Once that's there, take the silver 6mm screws and secure that in each of the corners. And then install the washer and the nut for the encoder. Now be sure not to over tighten this nut because there's nothing to stop it from cranking down really hard, and you could damage this circuit board if you crank it down too hard. So just make it snug enough to not come loose. Now the 3D printed knobs are for the volume control and for the encoder. The one with the index line on it is for the volume. Simply push them in place. Now the next step is to marry the control board and assembly with the RF board. Now if we turn this over, we can see there's the mating connector for the RF board, and here's the connector on this side. So these mate together like this. Note that this connector is pretty tight, so you're going to do it very carefully and slowly. Once you get it in place, these 4 standoff screws will be sticking through the board. Use these female standoffs to secure it in place. Okay, with that done, now we take the bottom print here and attach that. The large notch here goes around the BNC, and then this notch goes around the power connector. And it just slipped right over these standoffs. So now at this point your transceiver is almost complete. The only thing it's missing is the back panel, which is yet another circuit board. Now before we attach this though, there's a calibration and alignment process we need to go through, and we need access to the RF board to do that. So we're not going to put this on just yet. So the next thing we're going to do is start the calibration. Now the first step is to calibrate the 10 MHz reference. And there's a number of ways to do this. Jonathan in the manual recommends using a radio with a spot feature or a scope. I'm going to zero beat against WWV. That's what I can wind up doing here on my bench pretty easily. I've got a little receiver up over that way. You can't see. If I turn it up, you can kind of hear about a 500 Hertz tone or so. Maybe it's a little bit higher. That's tuned to WWV using single sideband, and I've adjusted so I can get that audio tone. You can just kind of hear it in the noise. And that's actually the carrier for WWV. So what I'm going to do is adjust the 10 MHz reference here, and when this 10 MHz reference and the one receiving from WWV match, I'll start to hear the beat, and then it'll eventually go down to 0 beat. So let's actually go do that. So now you just heard another tone come up, a higher pitched tone. That's from this radio. So bring that tone down. And now if you listen carefully, you can hear a wah 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 sound in the receiver. Wah 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 wah. Okay, so now I want to adjust this. I want to go to the fine scale. So now I push and hold. Now I'm at 1 Hertz. And now I can kind of try to bring that wah 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 sound down to essentially no zero beating. Now it's getting slower, wah, 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 wah. Now it's about once a second. Now it's about a 5-second cycle. That's pretty darn close right there. Now the next thing to do is to calibrate the IF, and basically just doing it but to maximize the response. Jonathan, to do this you need to inject a signal into the radio. I'm doing it with a signal generator here that's kind of up on the shelf above here, but Jonathan suggests a couple of other potential things you can use, like a nano VNA or a tiny SA, to use those as a signal source. So that's another way to go ahead and do it. So I'm injecting a signal here at 14.055, and if I turn that RF output on, you can actually hear the tone in the radio. And he suggests that if you turn on the RIT and adjust the RIT, you're going to hear a pitch change, but if you hear a volume change, that would indicate that the IF probably needs to be tuned. So I hear the pitch change, but no real volume change. Let's go the other way. Oh, it's definitely getting louder here. A good 30 or 40 hertz off, it's getting a little bit louder. So that indicates we probably want to adjust the IF. Okay, I don't really want to rely on my ears to detect volume changes, so I substituted my meter for the speaker so I can actually take a look at it. So if I go and do that same experiment again here, put the RIT on, and watch my meter as I go down a little bit, see how the audio level's coming up, and then it drops back down. So not super sensitive, but I've got enough that I can actually see a change. So I'll use the meter now to actually do the adjustment. Okay, so I'll go back into the menu and go to Cal, select, adjust it for IF, hit enter, and now I can adjust this, and I can see if I adjust it that way, my meter is going down. I adjust it the other way, the meter is going up, and it peaks and then comes back down again. Right about there seems to be the peak. So I think I've now aligned that IF. Now the final step is calibrating the power amplifier. And this is a critical step. You've got to do this very, very carefully. There's 2 adjustments. They're very small little potentiometers, so we've got to be careful with turning them. The first is to adjust a bias. And the second is to adjust the output power level. So the instructions are all pretty clear, that you'll start off by turning both the controls fully clockwise, and then connect a paddle and put it in straight mono or straight stereo depending on what you're doing. Set the band to 20 meters. Go to the calibration menu, change the PA OSC setting from enable to disable. So this will turn the RF off, so we can actually go and set the bias without outputting RF. And then we're going to hook up a DMM to the gate of the output FET. Okay, and it's shown right here where that is. So we connect up DMM here, and then pick up ground from our little ground strap on the crystals. And then you'll key down the paddle and adjust RV2 to get between 2 and 2.5 volts. And Jonathan's recommending between 2.4 and 2.5. So we'll do that step first, and then once we do that, then we'll change the PA OSC setting from disable back to enable, and then we're going to adjust the output power using RV1. So So we'll have to use an RF power meter and dummy load to actually go do that. And the final thing to note here is when we're doing this final step, the heatsink won't be on that FET because we've got the back panel off. So we want to do this in short bursts. In my case, I might actually find a heatsink in my junk box and attach it to this just to be on the safe side that I don't hurt anything. Okay, to get the radio ready for this, let's go to our cal menu, hit select, go up to PA OS enable, we'll disable that. Okay, and let's see what else we have. We can go back to the main menu and select the keyer straight mono is what I have, so keyer straight mono. Okay, so now we should be all set to be able to set the bias. Okay, I've gone in here and adjusted RV1 and 2 to be fully clockwise. I've got my key ready to go here with the radio keyed up. I should be able to adjust RV2 to get between 2 and 2.5 volts. So RV2 is this one right here. If I bring that down, see that voltage coming up on the meter here. So we'll bring that until we get to about 2.45 volts. That seems to be the target, between 2.4 and 2.5. So 2.4, that's a little bit high. Yeah, it's close enough right there, 2.45 volts. So now I've set the bias. The next thing we need to do is re-enable the output, connect up to a dummy load, and adjust output power. The final adjustment is to adjust the RF output power on 20 meters to be 5 watts. Unfortunately, I don't have a really low power slug for my Bird watt meter. I only have this 100 watt slug, which means that the 5 watt reading will be down here in the lower portion of the scale, and it really is not going to be very accurate. So I'm going to use a different method. I've got a 5 watt rated dummy load right here connected up to my scope. So that will absorb all the power. Now you'll note that some high-speed scopes have got a 50 ohm termination built in. However, it's not going to be rated to accept 5 watts of power in the 50 ohm setting. So I'm using the external 50 ohm 5 watt dummy load, and the scope is in a 1 mega ohm termination. So I'll measure the voltage directly on the scope, and I've got the scope set up to measure RMS voltage. Now 5 watts into 50 ohms is 15.8 volts RMS. So we'll make an adjustment to power until the RMS reading here reads 15.8 or something close to it. You got the screwdriver in RV1, key up the transmitter, see we're at 11.1, and we'll go counterclockwise here, watching that voltage come up, and right there, 15.8 volts RMS. That's our 5 watt output power adjustment. Okay, so now we're ready to close up the transceiver, and what we're going to do is take this thermal pad and put it on top of the transistor there, so it will become a good interface between there and this silver pad on the back of the board, and that will all go together, and then 5 screws to lock all that down. You may have just seen a portion of my contact with the Route 66 Special Event Station W6V, but my very first contact on the radio, as soon as I plugged it in, was with EA5 FID in Spain, so across the Atlantic Ocean from here in New Jersey. Second contact was N0 IPA in Colorado. So the rig's working quite well. Sensitivity seemed pretty good. I compared it to my Pentec TR45 and to my Kenwood TS870 that's up on the shelf up there. So I'm very happy with the radio. Please see the links down below for information on where you can get one of your own Compact Field Transceiver 1, CFT1 radios. Thanks again as always for watching, and we'll see you again next time.